Hi, my name is Miguel Suau and I'm presenting our paper, Offline Contextual Bandits for Wireless Network Optimization. This is joint work with my colleagues at Huawei Ireland Research Center. Okay, so what's wireless network optimization and why should we care about it? Well, in the recent years, there has been an explosion in data traffic, and this is due to the growth in number of users, but also to the new services that are now available, such as online gaming or video streaming. Users are demanding more capacity and lower latency, which translates into larger and more complex networks. These networks, however, are still operated manually by network operators who need to adjust the configuration parameters of every cell in the network. This is a very expensive and time-consuming process, which translates into configuration parameters that do not adapt to changes in the network environment. So in this context, we want to find a solution that would allow us to automatically adjust the configuration parameters, and we want to learn that solution from data. So we formulate the problem as an offline contextual bandit. We are given a network state, and that's defined by a series of performance management counters, some engineering parameters, and some contextual information. And given that state, we need to select the action, which belongs into a 14-dimensional action space, one dimension for each of the configuration parameters that we're trying to maximize. And our task is to find a policy that selects actions for every state and that maximizes a certain objective. And this objective, in our case, is the throughput, and because that's what we're trying to maximize, the average throughput per user, and we can use that as our reward signal. And as opposed to the online learning setting, we are not allowed to interact with the environment, we're not allowed to interact with the real network, and we can only learn this policy from a static data set. And this consists of samples of states, actions, and the corresponding reward. And these samples were collected while following an exploratory policy that is known as the login policy. Okay, so the first thing we do is we build a reward model. We learn a reward model from the data set. This is just a neural network that takes as input the context and the configuration parameters, the actions, and it predicts the throughput. Using that reward model, then we can just try to maximize it to find the action that gives the highest reward. However, this is a problem in our case because our state action space is very large, it's 14-dimensional, and doing exhaustive search is nearly impossible. So instead what we do is we optimize the reward model following the gradient ascent. And to do so, we take the gradient of the reward model with respect to the action, and then we just follow the direction of this gradient. And we can do that because the reward model is differentiable, it's just a neural network, and therefore we can just find the action that optimizes the throughput in such a manner. However, if we just did that, we might run into trouble because the reward model might be biased, which leads us to the second challenge, and this is data sparsity and covariate shift. Because our state space and also the action space are very large, we cannot rely on having a data set that fully covers such a large space. And we will inevitably have regions in this space that are underrepresented in our data set. And therefore, our reward model will be unreliable in these regions. Another problem is that because we're trying to learn a policy that is hopefully better than the login policy, we run into the problem of covariate shift. And this is because the action distribution of this new policy is going to be different from the action distribution that we see in our data set. So this makes even worse the problem of data sparsity. So we propose two solutions to mitigate this issue. One is counterfactual data augmentation by increasing the number of samples, creating these hypothetical samples. We're trying to make our reward model generalize better. And the second approach we take is uncertainty regularization. Instead of training just a single reward model, we train an ensemble, which is n reward models, and we use those to predict the throughput. So now we can also obtain an estimate of the uncertainty of these models, which is given by the standard deviation of those predictions. We can apply that as a penalty to the objective function to avoid converging to regions of the state action space that are underrepresented in our dataset and therefore are uncertain for our reward model. And the last challenge we face in this problem is computational efficiency. We want our method to be fast because we want to optimize many cells simultaneously. And running gradient ascent, especially on a reward model ensemble, might be computationally very expensive. So what we do, and we call this the hybrid method, is we use a pre-trained policy network that we train offline following the off-policy gradient. And we use that policy network to select good preliminary actions that we just need to fine-tune via gradient ascent. So this mitigates the computational burden and still leads us to find good actions that maximize the throughput. Our results are conclusive. We can outperform the logging policy while still being computationally efficient. So the plot on the left shows a comparison between the logging policy and the policy network that we trained via off-policy gradients. We can see that the gain is relatively small, but when we combine this policy network with gradient ascent, we can obtain much higher gains. So the plot on the middle is a comparison between gradient ascent with random starts, that's the orange box plot, and a gradient ascent while starting by the actions suggested by the policy network. And this is the blue box plot. And we do that, we show here the performance for 1 and 5 and 10 random starts. Of course, the performance increases as we increase the number of random starts. And we see that both methods perform very similar. However, gradient ascent with policy network, gradient ascent when we start with the action selected by the policy network, is much faster. The reason is that the policy network already selects good actions that only need to be fine-tuned. And this is supported by the results that are shown in the horizontal box plots on the right. We see that the wall clock time when we use the policy network to select preliminary actions is shorter, and we also need to run fewer gradient ascent steps to converge to a solution. So all in all, this is still an appropriate solution. This is still a solution that brings us closer to the optimal, but it's still computationally efficient. Okay, so this was just a short summary of our paper, of our method, but you can find more details about it in our paper, and please feel free to contact us if you have any questions. Thank you very much for your attention.